That's the first topic. That is how to make a confidence interval for such a proportion. We're going to have a little bit of background here, but here's the tool actually right away. And you had 30 seconds to Google this tool and apply it in the context I was giving to you. So that, of course, was not possible. It may look a bit tedious, but it's not too bad actually. Look at this. We just have the two numbers, x, that would be 600, and the n, that would be 1000 in this example, right? So we have the proportion, sometimes we would call that p hat, plus minus 2 times the standard error, in a way. The 2 is the quantile. I think I actually, let's see, no. So plus minus 2 times this number, which in fact is the statistical uncertainty of a proportion, or the standard error of a proportion. And it says the proportion minus and the proportion plus. So it's the proportion plus minus the same number here, right? And this is this bit odd thing, even though I started out by making the link to the binomial distribution, which we have. I mean, the formal setting for this random phenomenon that we're talking about here would be a binomial. But nevertheless, we apply a formula that comes basically from the normal distribution, and that is because the normal is a pretty good approximator of the binomial probabilities, so that can make sense. That's the reason why. There are formal rules and theories, but this is the short version. However, we have an additional thing going on today. So today's a little bit special compared to all the other times, actually. Today is the only day we talk about statistics for these count data, categorical data. And the tools we will use today is based on normal distribution, and then we're going to use the chi-square distribution as a consequence of the normal thing. However, for all we do today, these tools are only approximately okay. So whereas back in the old days, 1 and 2 and 3, 4 weeks ago, the assumption was that the data followed a normal distribution, or then at least if n is large enough, probably many of our tools are still okay. That's kind of the line of thinking. Now today there is really no normal assumption of the raw data going on. It doesn't make sense with categorical data where we count something, binary outcomes. They are not normal. So there are really no real distributional assumptions today, but there are some approximate thing going on that requires, for those tools that we are using today, for all of them, there will be some requirements that n should be large enough for those tools to be valid. Otherwise, you don't have the tools to actually do it, with 1 or 2 little exceptions that we'll get to. So the rule of thumb is that we would say, what about our 600 out of, that's 60, that's actually 600 and 400 then here. 600 and 400, are they greater than 15? Well, by far. So our tools would work nicely for the 600 out of 1000 because they are way into the nice area of being applicable. That's a bit extra today. We're going to check that the n is large enough to make sure we can do it. A bit of background just in the beginning, and then we'll fly out there. What you are looking at here is based on the basic probability theory and methodology that you were taught when we talked about the binomial distribution quite some weeks ago. Because the mean of the binomial looks like this, and the variance of the binomial looks like this. And if you recognize, yeah, well, let's do the next one to be, when the mean of the binomial is how many malformations, which if we go back to that example, how many malformations would there be in 1 year? Well, that's the actual absolute number, whereas the proportion is simply the binomial number divided by n. And that's the one we're interested in. So the mean of the proportion, or I should say the estimated proportion, luckily, is the population proportion. We never had any other idea about this number. Of course, that's what goes on. To compute the actual proportion is the right one to compute, to estimate the population proportion. We wouldn't have thought otherwise. Then what we can do to be intelligent about the proportion is that we can quantify the variability level, the uncertainty level for such a proportion. We can compute the variance for the proportion, spelled out here. And then we use the variance rule, and we see that the variance of a binomial proportion, it becomes this one, but divided by n squared. So all together it becomes this one. And this is exactly the number which is used in the formula here with the square root, right? P times 1 minus p divided by n. That's the standard deviation for the proportion coming from, so it's binomial theory that gives the formula, but combined with the normal distribution. But it's the binomial standard deviation which is used in the formula. That's the explanation, a bit of background. Let's do another little example that I often do. You didn't see the other one. So we do a little asking out in the auditorium today. How many of you guys, and guys in the American way, that means every one of you, are left-handed? Show your left hand, of course. I count. 1, 2, oh yeah, good. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Good. How many of you are in here all together? Raise all your hands. Whoa, then we'll have a 10. No, we'll not. I counted to 100. Here's the result of the survey I just did. Oh, you didn't see I just did very rapid data import and analysis here, integrated from my brain and into the computer here. With 10 persons out of 100, I start out by computing this standard error, the statistical uncertainty about a proportion of this type of 10% out of when we talk about 100. That proportion, and this, if there's one thing to remember in this course, I've said that a couple of times. Hopefully you remember more than one thing, but nevertheless, this is a really, really useful little thing, easy thing to remember. Whenever you see a proportion in the newspaper, and you couldn't open one newspaper without seeing some percentage or proportion, then please think about, before you start running out and doing some investments or making any decisions in your life based on this proportion, or you run out and kill someone, or you, whatever you do, run out and vote for someone you shouldn't vote for, or whatever. Think about this formula, right? Take the proportion times 1 minus the proportion and divide it by n. And if they didn't tell you what the n was, then forget about using this number for anything. And then you know the uncertainty of this percentage. This is the percentage uncertainty formula. Whenever you're given a percentage, use this formula to quantify the uncertainty of the percentage. It depends on the percentage itself, that's the p, and it depends on n. But two very simple numbers, right? You know the percentage because that's what triggered you to make the thinking. You just need to know the n. We can take that and then combine it with the standard normal percentile. The first percentile you should remember in this course, right? 1.96, that's the percentile in the normal that gives you 2.5% in each end. So that's the one we use to do confidence, 95% confidence intervals. So, percentage of left-handed in Denmark, taking you as a sample of Denmark with all the problems of this, is between 4% and 16%, right? We do statistics for something which we talk about in percent, and then we may have some p-value later on that is also percent maybe. So that's the challenge of today. Here is a remark. Actually, actually, I had a problem that I ignored. Maybe I was a bit fast. I should have asked you, of course. We had the problem that we actually had a 10 outcome here, which was not above 15. So actually, if I were very strict on this rule, I couldn't apply my formula. I shouldn't have, I'm too far out in the tail for the formula to actually, according to this rule of thumb, we're allowed to use the formula. But then we have actually a better formula that works basically for any size of n and p, x and n, I should say. It's a bit funny thing, so let's not dwell on it. It looks really spooky or questionable. If you take the rule, if you think, what should you do? I have a problem with the sample size. Hey, I just add 4. It's too small, so I add 4. And I'm okay. Of course, that sounds ridiculous when I say it like that. The thing is, it's based on pretty hardcore mathematical theory to identify that this is an order higher approximation of some Taylor approximation that can be approximated easily by this +2 rule. So it's based on pretty heavy mathematical theory that comes out with a simple solution of a better approximation to make this distributional assumption valid. And it's easy to remember. It's the +2 rule. +2 successes, +2 failures. That gives a better approach that basically always works. It doesn't change results dramatically, and it would indicate to us that when we have a 10 and 90, it doesn't really invalidate the original formula sort of drastically. Let's see. Are you ready? 60 out of 100 now. Just apply the formula. Or think. Well, I'm happy I was not planning to submit this to Journal of Statistical Education or anything, since I really ruined you guys with my bit of theory there on the confidence intervals. No, of course it's okay. I'm actually wondering if I did this correctly, so let's check. We're getting back to these functions later, but let's just check to be sure. What did I say? 60 out of 100, right? Let's just forget about this one and forget about this one. No, my example in the Kahoot, that was 60 out of 100, right? Do we agree on that? Let's see what the result is. The result is, we can see the fifth. This is applying exactly my formula, almost exactly with the version here. So plus minus 10%. Was that the one I chose? I was okay, actually. I realize this is difficult because we cannot do the formula in 30 seconds. But I'm also getting this to let us getting used to the level of uncertainty here. When I look at proportions out of 100, it's around plus minus 10% when we do a confidence interval. Plus minus 10%. It's not very precise out of 100, right? With 1,000 before, it was plus minus 3%, right? 3 percentage points, if you want to be exact there. So we have to get used to this level of uncertainty. Who the real slim guy there? Good job. That takes us